So yesterday we did all this technology about Monte Carlo, etc. And today I'd like to give you two examples of what you can do with that. And one is frustrated magnetism, which comes at the end. And this one is then a dimensional mismatch Kondo system. So you heard in the former talk that, we can only do half filling. That's true, right? And so how do we get metallic states? And that's a trick if you want to get metallic state without confronting the sign problem. And it's a trick, and it's also experimentally relevant and motivated. So what we're going to look at is our spin chains on metallic surfaces, or basically heterostructures, if you want, where you have a layer of spins embedded into a metallic environment. So this, I'm only going to talk about this because I won't have enough time. So let me start with the motivation. Why did we start this? This really is motivated by some very beautiful experiments by Sander Otte in Delft. And what he does is he has a copper 100 surface, and he puts a sort of, I think it's copper nitride insulating layer on top of that, and then he puts cobalt. Right? And the cobalt has a spin 3/2 spin, and there's a spin 3/2 atom, and there is an easy axis anisotropy just because there's spin orbit coupling, which has to be there, and it turns out to be positive, such that the Kramer doublet plus or minus 1/2 is actually. I have to change glasses. I don't see my slide. This is much better. Okay, so this is a Kramer doublet plus or minus 1/2, and you have a very nice Kondo resonance. Importantly, the scale here is 2 millielectron volt, so it's small enough so that you can put in a magnetic field in the lab and break the Kondo. Very important for very nice if you want to do understand the theory, to have some parameter which breaks the scale so that you can see what the scale is. And this is what happens, when you put in a magnetic field. This Kondo resonance is broken. You break time reversal symmetry, and that's breaking the symmetry, which sort of protects your Kondo. So we can. This is a when I look at this, right, I see this, right. This is the model. You have a conduction electrons, which are basically the copper 100 surface. And then you have an impurity spin, which is this S, which I'm just taking the doublet here. So this is a model, if you want, just for this energy scale here. We're not looking at the excitation to the 3/2, multi-Kramer, this one is 3/2. And our Kondo here, and then we put in a magnetic field, which is coupled to the Z. So we can get, our Kondo resonance by looking at the spectral function of the composite fermion optic, which we've heard a lot about these last days. Okay? So now that's nice. It's nice to have a Kondo, right? It's amazingly clean, right? It's an amazingly clean experiment. When you talk to other experimentalists, they see Kondo, but it's not so clean because, and I think it's very clean because the cobalt atom is placed on this decoupling layer, right? That's my understanding. And so now what they can do is remarkable. They can come and they can build chains. So they build chains up till 9, and so for us, building a chain means we just add an R to the spin. We have a spin which is just, this is the cobalt atom. R is a cobalt atom. And also they tell us that there is a magnetic exchange, direct magnetic exchange between those cobalt atoms. So we put this into the model and we have a magnetic field. So what they do is this is experimental data, which is, again, I think beautiful. Here you see that this is dIdV, basically as a function of the voltage and the magnetic field. So this point here is this resonance here, and then when you put in the magnetic field here up there, you pop it up, then basically the Kondo resonance splits up into 2, and here you're fully saturated, right? And so now you put in the 2, right? You put in 2, and what happens is that you have a field-induced Kondo effect. Essentially, when you can start just looking at 2 spins here, like this, start with this term here, and you have a singlet ground state and a triplet excited state. You put in a magnetic field. There's going to be a critical magnetic field where there's going to be a level crossing between the triplet and the singlet. And at this level crossing, which is denoted by that, you have a field-induced Kondo on these 2 spins. You can continue, right? And then you can do it for 3. You have a Kondo effect, I think, on the 1 and 3 without field, and you have a field-induced Kondo effect on the atom 3, etc. And you can go through this. Now, what we did is to say, well, what we can do is do numerics, just redo this, but what we do is, because we don't want to do maximum entropy, okay, so that's maybe hard. Maximum entropy, going to real frequency in Monte Carlo in general, when you work on imaginary time axis, is very hard. So what we do is to just look at the 0 frequency. That we can do. And you see that, okay, this is Monte Carlo, this is experiment, and there's a beautiful match. I'll work you through this. This is the Kondo resonance, which we see here. This is as a function of temperature, and you see that you have a peak here, which tells you that I have a point here, right? And as I go away here, as I go away from as a magnetic field, and I lose this intensity. So there's intensity here, and it goes away. So this is this curve which goes down. Then here, if you go at the 2 impurities, you see that I have a peak here at a finite magnetic field, which corresponds to my level crossing. And if you have the 3, you have those peaks here at 0 frequency on the 1 and 3 atoms, and the second here when this level crossing set. And you can continue to 4, 5, 6, 7, and then we stop because it was too hard. Right? Okay, so this is something which tells you that this model here has some sense of reality. That's all. It's a model which you can simulate and which you can really compare to experiment. That's very satisfying. And Bim Ladanu is the person who did all the work. This is beautiful work. Right? So now we imagined that we could ask the experimentalists. We asked, but we got no reply. That instead of doing a chain, they get a circle, right? They get a circle, and they get rid of these dominant open boundary conditions. So that would be very nice. And then you can start thinking of chains, right? Chains on metallic surfaces, and then you ask the question of what happens. Okay, so this is the motivation to look at that. So now the simulations we're going to do is we have a 2D system, right? And we're going to put a chain, and everything's going to be on a torus. So there's no boundary anymore. Okay, so let's start and see what happens to those models when you go to the Kondo phase, right? So to JK is very big, right? So JK is very big. You go into the Kondo phase, and then we saw yesterday and that we expect a heavy fermion. That's what I would call this. And now, how do you see this? You see, well, if I look at the spin-spin correlations here in the Kondo phase, then you will assume you would expect that the spin-spin correlations of you're measuring spin-spin correlation on the spin 1/2 chain. So in principle, they go as 1 over R if the spin the chain is isolated. And here they will go in the Kondo phase, the spins become iternerant. We talked about this composite thing, etc. And they should basically in space and time, inherit the behavior of the conduction electrons. The conduction electrons are basically now just basically now the metallic host. So this is done for this 3D case. You see that in 3D you can work it out. It's 1 over R to the 4 for space. It's 1 over tau to the square for imaginary time. And you can calculate this, and you see that we get this. So this is the same thing which happens for all these topologies. The Kondo phase is just basically a phase where you have injected into your count of electrons the spins, right? So if you count now the number of electrons you have here in this Kondo phase, you would have to count the conduction electron phase plus the spins. And that's what we would call the heavy fermion in these dimensional mismatch systems. Okay. So now what happens for weak coupling? So strong coupling is nice. It's a Kondo metal. What happens for weak coupling? And there things become really, really interesting and case dependent. So how do we do that? We say, okay, we're going to try to expand in JK. So if we expand in JK, JK is small, then we can integrate out, essentially, we can do is integrate out the fermions, right? So we're going to integrate out the fermions. If we integrate out the fermions, we get an action, which is first the action of the spin 1/2 chain. So that's a spin 1/2 chain, and something which we will call a dissipation term, right? Because the fermion, so this is the spin 1/2. The way you do it, the way I did it here, basically, is to put in a spin coherent state, right? So this is basically a vector, so that corresponds to a spin, which can talk over space and over time via this spin susceptibility of the host metal, and this is perturbative in second order in JK. Okay, so now everything is dependent on the form of this, right? So we can now go to 1D, right? So this is now case dependent. So in 1 dimension, so this was on the slide before, nothing new. In 1D, what we're going to do now is going to say, let's sit at the Heisenberg chain. The Heisenberg chain is a CFT, it's a critical point. And we know that the scaling dimension of the spin is 1/2. So that just means that the spin-spin correlations decay as 1 divided by 2 delta n, which is then 1, okay? So we know what the scaling dimension is of the n. And then we're going to ask ourselves, we know that it's Lorentz invariant, etc. And then what we will ask is, is this term relevant or not? We just do power counting. And what we do is, okay, so what we have to know is how does this object react? And if you take a Dirac system has a 2 plus 1 dimensional Dirac system has decay in imaginary time, which is tau to the 4, and also decay in real space, which is r to the 4. So let's just consider the equal time and imaginary time correlations. So you will see that if I take this term here, and I do a scale transformation, r goes to lambda r and tau goes to lambda tau, then I will get a factor lambda, 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 lambda to the cubed. These two, from these two, I'll get 1 over lambda, and from this, I will get a 1 over lambda to the 4th. And if I didn't mess up this morning, it's lambda to the minus 2, right? So that means that it's irrelevant, right? So if lambda gets bigger, it's irrelevant, so you can just forget this. So what this means is that we can sort of guess the phase diagram. At at small jk, this spin chain is going to stay a spin chain. It's not going to talk to the conduction electrons or to the metal. And when you go to the large jk, then you will get a Kondo heavy fermion. So these are typical results we get. How do we see this? So this is spin. This is just the Heisenberg chain, just a Heisenberg chain. These are the spin structure factor, it's called. It's peaked at pi. And if you do that in real space, you get something which is 1 over r. So this is space, right? So this is the 1 over r decay. If you go up to jk 1.5, it's remarkable to see that, this is a big coupling, right? The bandwidth is 3 because it's a Dirac system. This is a huge coupling, and you still have something which is 1 over r, and you barely see no difference. What's remarkable also is what you see if you look at the dynamics. So yesterday we talked about fractionalization. You talked about fractionalization and the fact that these are 2 spin-on continuums, right? So when you do a spin flip, it decays into 2 spin-ons. And this is a very well-known picture, at least in our community, about this 2 spin-on continuum, which has been shown also experimentally, right? So this is what you have to see here is that, okay, what is a 2 spin-on continuum? It's linear here. There's a lot of weight here. It's linear here. It has a power law decay when you go like that, and there's a lot of weight around like that, right? So just look at this picture and say this is a 2 spin-on continuum. We can talk ages about this. I don't want to go to this. What's interesting to me is that I put in a JK 1.5. I do the simulation with the same caveats, right? This is Maxent, et cetera, the same caveats. And I get exactly the same thing. I would dare you to see a difference between this and this. Right? So there's no difference. That means really that the spins don't talk to the conduction electrons, etc. So that's a Kondo destruction. That's what we would call a Kondo destruction. Then you go on, and then at one point, you lose spectral weight. The spins becomes itinerant with the process of generating this new quasi-particle, etc. Okay? So that's very nice. And what you can also do, and this is the former things were done by Bimla. This is now being continued by Shonak Biswas, who's now joined our group. And what you can do is also look at the spectral function, if you want, of this composite fermion on the chain. And you see that in the heavy fermion state, then you have a very nice dispersion, right? So this would be the dispersion of a quasi-particle. And when you go at weak coupling, this is where we're in the Kondo breakdown phase, you see basically that you lose the weight. So you really see here by measuring spectral functions of the Kondo of this composite fermion, which we talked about yesterday, that you are sort of observing some type of an orbital select. Well, let me not put words on this. This is just basically you're looking like that. You're going down to the Kondo breakdown, and basically this weight is just breaking up. Right? You're breaking up the quasi. That's all. Okay. So this is the first result we have. We believe that this nice model, which is it's a toy model because it's not being realized yet experimentally, but it has a very nice realization of a Kondo breakdown transition. We have one heavy fermion phase where you have the condensation of this boson, which the B, which Rebecca talked about before, and also no magnetic order because it's a liquid. And then also here you have a Kondo breakdown. B is equal to 0. The two systems are decoupled, and I have also a no ordering because it's a one-dimensional liquid. So this is like a mini type FL star. So we're fascinated by this transition. We're doing much more work. We want to look at critical exponents. This is a unique realization, in my opinion, of a Kondo breakdown transition, and there is a lot to do about try to understand this type of transition with entanglement measures, entanglement witnesses. So this is things we are still doing now. Okay? So this is the first case of a Kondo breakdown transition, which you can realize on these systems. Questions? Yes. Yeah. Can I, yes. Can I what? Can I? The last term is already this one? Yeah. Yeah. Well, it comes from, we motivate it from experiments, right? There's no, it's already dynamically generated, but this was our motivation, that we took a J, we wanted to look at these cobalt atoms on copper 111, and we just needed this J term to be able to reproduce the results, the experimental results. So on these surfaces, the experimentalists tell us that there is a direct exchange. That's all. But in principle, you would say, I mean, in principle, it should be dynamically generated. Just it's not an independent scale. So you have to be careful to see if it's big enough. That's all. So we just motivated. We started with this and then continued to see what we could get. So of course, this J is built in. Good. So now what happens? So this is more tricky, right? I'm changing my semi-metal. The surface is not a semi-metal, it's really now a metal. So this is what happens, I mean, if you would copper 100 surface. That's more realistic. So we started with this project, and it took much more time because it's much harder. And why is it much harder? Because you do the same calculation as before, and now you are in a metal, in a 2D metal, and your imaginary time goes of this spin susceptibility goes as 1 over tau to the squared, and in real space it goes as 1 over r to the 4. You can do the same calculation as before. If you remember, before I had a tau to the 4, now I have a tau to the 2. Here I had a lambda minus 2, the lambda minus 2 goes away, right? So essentially this tells you that this interaction is marginal, right? So you do a scale transformation, nothing happens, you don't know what to do, right? You're just stuck. You have to do simulations, you have to know, is it markedly relevant, markedly irrelevant? So the question of, this poses the question, which was, to the best of my understanding, not completely understood, is what happens to, it's a pretty fundamental question, right? You take a one-dimensional spin one-half chain, you put it on a metal, you ask yourself the question, what's going to happen? It's not clear, right? So Manuel Weber has so we did this, right? We did this, we say we have to take a detour, we can't continue with the project. And then what we did was to say, we're going to just simulate this action. So what goes in the computer is this. What goes in the computer is a Heisenberg spin one-half chain. For each point, for each site, we have a set of bosons. These are vector bosons. These have SU2 symmetry, and we sum a lot of frequencies, right? So each site has its own bosonic bath, okay? And then we couple this bosonic bath like this, right, to the spins, right? This is a vector. And so this is not Fermion Monte Carlo. This is done with stochastic series expansion with retarded interactions. Manuel Weber developed a beautiful code which can solve this problem very nicely. So I won't go there. This is not auxiliary field. That's all I want to tell you. And Manuel did the calculations. The only thing which is important for us is that in the calculation, you don't really care about this. The only thing you need to know is the distributions or the spectrum, if you want, J of omega. And if you want to generate an ohmic bath, or if you want to generate a tau minus tau squared in imaginary time, the bath has to go as omega. Okay? So let me repeat it. This is a spin one-half chain. Each spin one-half degree of freedom sits in an ohmic bath, right? And that is supposed to, this ohmic bath is supposed to tell you this would arise, if you want, very naturally from a metallic surface, right? The only thing we're neglecting is this, which is in principle irrelevant. Okay? So this is what we're going to do. And the first thing you realize is that a bosonic bath cannot screen. You cannot. And why is this? It's actually pretty simple to see. Is that if I take only one spin one-half and I couple it to a bosonic bath, so just bear with me, and there's this. Forget about this I. Then there is a conservation law. The concept of total angular momentum, Q that cross P, that's angular momentum plus integer angular momentum, and this is one-half angular momentum. Your J tot will be, this is a conserved quantity, you will never get a singlet ground state out of this. Right? So you cannot screen a spin 1/2 with a bosonic bath. And so the question is what will happen. So these are the results. And it's one of these things where numerics turns out to be very hard because you're looking at something marginal. Huh? When you're looking at something marginal, you have to have huge lattices to see what can happen. So this is as a function of alpha. Alpha is the coupling to the bath. And this is what you call a correlation ratio. This correlation ratio is a very nice quantity which will allow you to detect if you have long-range order or not. Right? So what it is 1 minus SQ is the ordering vector plus delta Q. That would be 2 pi over L for a finite system divided by S of Q. If you have a disordered state, then this object is a S of Q is a continuous function. And so when delta Q goes to 0, this goes to 1, and this is basically 0. If you have an ordered state, this thing here diverges much quicker than this, and so this something here goes to 0, so R is equal to 1. So R is 1 in ordered, R equals 0 in a disordered phase. So what you see if alpha is big, then the simulations here, if alpha is big, right, then I go to something which is ordered, right? 22 here, 22 up to the bigger size here. This is 322, something like that. So this is going up. The problem is, so this is ordered. And then what you see is that there is a crossing, right? There's a crossing which telling me that there's a sort of a critical alpha between order and disorder. And this crossing is always slipping to smaller values of alpha when I get my bigger system sizes. So I'm not converging. The other thing you can do is to say, well, let me consider a given coupling. I consider a given coupling, and I'll make the system size bigger and bigger and bigger. And what you always see is that, let me take one of them for you here. So this is a given coupling, 0.2. This correlation ratio goes down, so you seem to be going to something which is disordered, and then you've hit a minimum here, and then whoop, it starts to go up again. So there's always a scale if you want. There's always a scale below which you will see some type of long-range order. That's the claim. Right? So that's it. So this is telling us that if you couple a spin chain to independent dissipative baths, ohmic baths, then it will become a long-range order. You can also, so this is Monte Carlo. You may, yes?
Yeah. Regarding the bath you're talking about, is it the virtual bath? I mean, you say bosonic bath, right? Can you consider it as an ensemble of, let's say, phonons?
Yeah, this is it. This is really what goes in the computer. These are an ensemble of harmonic oscillators. Right? It's just an ensemble. Sorry?
It's not a virtual bath.
No, it's not. It's really there. It's really there. It's just these are independent harmonic oscillators. The only thing which, so of course in the simulation, the trick of the simulation is that you can integrate out the bosons. When you integrate out the bosons, you get a retarded interaction just in time between the spins. And the only thing you need to know for this retarded interaction is the spectrum, J of omega, right? Once you know that, you're done, right?
And is there any reason you're considering just the leading, the leading spin phonon, let's say, coupling is just linear there, but you're not considering, let's say, nonlinear terms for a dagger plus
For the A dagger, so you mean this term here, or this one?
Yeah.
This is the simplest term I get, and this is the term which reproduces what I want from my motivation. But we could maybe do more. I'm not sure. If you have something specific in mind, you should contact Manuel. He'll be very happy to try to see if he can do something else. This is really motivated. This work is really motivated from this, right? Coming from the fermions and motivating it. Okay, so now you can also do spin waves. I won't go through this. This is too much. But you can also do spin waves, linear spin waves. And it's a very nice calculation. You see that linear spin waves, if you do that in a bosonic, with this dissipative bath, then it's stable, and you can look at the spectrum, and what you will get in the spectrum is something which, like, these are basically it's a dynamical exponent z equals 2, meaning that if you look at the spin dynamics, you won't see your linear thing here. You will see something which is squared, right? Something like that. So you have a z equals 2, which you can pick up very nicely in the dynamics. Okay, so now I'd like to show you that this is what we get. We have a dissipation. So we have now two different phenomena. Kondo, which would like to have a a heavy fermion, and also dissipation. Dissipation drives you, in this case, to a long-range magnetic order, right? And our claim is that this model here, where you have the conduction electrons are just a half-filled Fermi C, that we have dissipation and Kondo singlet formation compete and trigger an order-disorder transition without any type of Kondo breakdown. So I don't know if I'm going to go, how much time do I have? I have more than half an hour. Okay, so this is a hard thing. So let me tell you how we did it. It's hard because we're looking at transition. We have no idea what is the dynamical exponent of the transition. We're looking blind, right? So this is the best way we could do it. And the first thing is to locate where's the transition, right? So where's the transition? This is d of f over d of jk as a function of jk. This is the second derivative of that, and we see that at 2.1 there's something happening. So we see, yes, there seems to be a transition at jk 2.1. Now, if you want to do some scaling, we better have an idea what is the dynamical exponent. So what we do is we place ourselves at jk 2.1, and we measure things in real space and see that there is like a 1 over r dk, and then we measure things in imaginary time and see that there is a 1 over square root of tau dk, right? So space and time are different, and in this case, this corresponds to a dynamical exponent, a z of the order of 2. So now that we have the jkc, then we have this, and then we have the z equals 2, then we know how to do some scaling, some collapse, right? So again, this is the correlation ratio, which I talked about before. The nice thing of this correlation ratio is that it's a renormalization group invariant quantity. That means that if you forget about corrections to scaling, so let's put this omega going to infinity, which is not the case in general, but let's forget about it for the moment. If you scale your inverse temperature beta as a function of L to the z, and then you will have this object should, and you put yourself at jk, at jkc, then this object should be a number, right? So this should give you a crossing point. And sure enough, this is very hard because we're working with a marginal operator, which will trigger, if you want, the order. So we claim that, yes, there is a crossing at 2.1 around here. That's what we saw before. If you go above, you have no order. If you go below, you have some type of ordering. So this is what we have, right? So this is not the best data we have, et cetera. Well, this is the best data we have, but it's just hard. And then if you go too much to small jk, then we don't have big enough system sizes to be able to see that this is going to generate some type of long range. Okay? Now, the thing which I think the most fascinating is to see this, right? Now, let's do the same thing. We start again with our two spin-on continuum, and then we place ourselves in this phase, which we say it's ordered, it's dissipation-induced ordering. And I hope that you agree that you see something which is not linear here, it's something more like square, right? So you see here those Landau type Goldstone modes, and if you go to big JKs, then basically you get your heavy fermion. We also looked at this quasi-particle. I will skip this. We claim that the single particle spectral function of this composite fermion keeps low energy spectral weight, even in this ordered phase. So we claim that there is no Kondo breakdown. So this is another phase transition, which we get in these dimensional mismatch systems, where we go from a heavy fermion, right, metal where B is not equal to 0, to an antiferrometallic metal with also a heavy fermion particle. So this is like a type of Hertzsprung type transition, I suppose, but in this dimensional mismatch setup, which still needs to be understood. Okay, so this is the summary for these dimensional mismatch. I will skip this one, right? But my claim is that it's an interesting playground to look at quantum criticality in heavy fermions. In a very special setup, granted, but nevertheless, you can do that without any approximations, and that may be interesting. Question? Friday morning.
Sorry, can you explain a little bit the concept of Landau damping for Goldstone modes?
If you have a Goldstone mode which will go into a particle hole continuum, it can start damping. That's all. Like maybe you heard about your plasmons, right? The plasmons, they're well defined when they are at small Qs, and then when at larger Qs, they go into the particle hole continuum and they Landau down. The same thing which happens, right? hope I did not. Yeah. Okay. Good. So now let's go and move on to frustrated spin systems. Right? So this is a case where, so we have up till now avoided the sign problem, did our things without the sign problem. Here, this is a case where we're going to confront the sign problem and show that we can really be useful to our colleagues, Kim and Brad, right? Because we could explain some of their experiments. That's really nice. I mean, normally we're not very useful. So there, we're useful for once. It's really nice. It's a good feeling, right? So this is work which was done by Toshihiro. We started like that because because it started because a person who I know well, Jose Valenti, told us at a conference dinner, that's why it's important to go to conferences, not for the talks, for the dinner. Very nice dinner yesterday, actually. So that in principle, you can do anything for kita F. It's such a hard problem. If you go to beta j equals 3, you're in business, right? So he said, okay, I mean, if Jose tells me that, let's try. So we tried and did this. So this is the kita F Heisenberg model. And so I'm sorry, I think you talked a bit about the kita F yesterday. So this is the pure kita F model, which is remarkable, which is completely frustrated and which has an exact solution in terms of Majorana fermions and fluxes which are stuck, right? That's why there's no dynamics of the fluxes. That's why it's such a nice, it's a possible, I think it's amenable because of that to an exact solution. And this is the Heisenberg term, okay? So this is on a honeycomb lattice. There are these X bonds, so they have SX, SX. So this is just the X here, the Y, and the Z, and then this is just a Heisenberg. This is a vector S dot S. Okay, so how do we want to simulate this? So this is trial, right? So we know how to do this without a sign problem. Doing this without a sign problem is writing these D's again. So we talked about this last time. This D is basically so I'm sorry, I went too fast. We of course fractionalize the spins like this. We have Rykosov fermions because that's all we know what to do, and we impose the constraint again with the Hubbard U. So this term here, right, with the D like this, corresponds exactly to my spin. And then this term here, because I'm having a spin 1/2, so how do I decouple this? I always need my perfect squares. And one way to do it is to say, well, I can, if S, this is a spin 1/2, if the constraint is imposed well, if I square this, it's going to be 1/4, right? So this I can forget, the square of this I can forget, the square of this. And then here I have the term here between the two gives me my 2K S dot S, okay? So that's pretty easy to see. So of course, when I do that, I have some freedom. I have this freedom of this S delta, which can be plus or minus 1. You agree, right? So I can put plus or minus 1. So for each bond, I can choose. I have 3 S of deltas, which I can choose. And of course, we're going to impose the constraint exactly, etc. So we're going to ask ourselves the question. Now we have a model which has a sign problem. But we have a formulation which has a minimal degree of freedom for a parameter, this S of delta. And you remember this slide maybe yesterday. Well, what I told you, this alpha, and somebody asked a question about what alpha is. Alpha is, of course, a complicated function of my formulation, in this case, my S of delta. And so we can ask ourselves the question, are there some sets of S of delta where the sign problem is not so bad, such that we can do some simulation? Right? That's all. We don't really have any, to be very honest, we don't have any a priori knowledge. If I give you this path integral, I see no way of predicting the answer apart from just doing the calculation. So this is the status we have for the moment. And here it is. So if I take all the S's plus 1, right? So I'll take a step back. I'm simulating this model, and I'm doing a parametrization in terms of just an angle. I'm saying that K is equal to A sine of phi, and J is equal to A cos of phi, and A is basically this object here. So we're going to put T over A equals 1. So T over A defines my energy scale. T over A is equal to 1. And I will look at the angle, right, which gives me how much K and how much J I have. So these points here are the pure kita F points. This is a ferromagnetic kita F point. This is a antiferromagnetic kita F point. This is the Heisenberg model. This is a ferromagnetic Heisenberg. This is the ferromagnetic Heisenberg model. This is the Heisenberg model, etc. So now let's go back. If I put all the S's to 1, then I get this average sign, right? I get this average sign. It's very bad. I can give up. right? I mean, I needed beta A is equal to 3 to be in business. That's what Jose told us. So this is not good. Now, if I do an Sx equals 1, Sy equals Sz equals minus 1, then I go from here, right? This is for an 18 site, right? This is for an 18 site. I go from here to here in the sun, right? So that tells me I can do my simulation. That's it. Right? So that's at the Kita spin liquid point, which is the hardest point. Okay, so we can go down and in temperature using this trick, and you can see that these are exact annualization results, which have an approximate phase diagram for this model. So here you have a zigzag phase. So we do see these are spin-spin correlations. So we do see my point I'm trying to make here is that we can go down to temperature so that we see the short-range magnetism, right? So we do have an information on the short-range magnetism. We can't go much lower than that. So we do have short-range magnetism of the stripy phase, or the zigzag. This is the zigzag phase. This is the stripy phase, which is, I think, around here. And then we have those antiferromagnetic Kitaev points and ferromagnetic Kitaev points where we have basically no correlations. Okay. So that's it. We can find a fermionic Monte Carlo method to do that. So this is a Monte Carlo method. I think it's the only Monte Carlo method that can do the Kitaev model. Of course, there's away from the Kitaev point where there are some very specific methods done by Motome, etc. Okay. So what is it good for, right? We didn't learn. Actually, there we wrote the paper. We're very happy, but people told me very nice, but we didn't learn anything. Correct, right? They're correct. But don't give up. So then we came and talked to Brad and Kim, and what Brad and Kim they measured the magnetic, what do they call that? The magnetotropic susceptibility. Oh, that's a crazy word, but in principle, what they do is they put a magnetic material on a cantilever, right? So a cantilever has a resonance frequency. They put the magnetic material on the cantilever, and they measure the shift in the resonant frequency because of the material. And they claim that this shift, they can measure this shift very nicely, and they claim that this shift is related to the second derivative of the free energy with respect to the twist, the angle. So here's my magnetic field. So my magnetic field is here, and I'm going to fluctuate like that my crystal. Okay. So this is the object we have to calculate. So this is just Kubo, right? So you just d squared of f over d of f theta. You just have to do the calculation, and essentially what you will get is this object. So this is actually the torque, right? So this is the torque these are the fluctuations of the torque in a certain sense. Okay. Good. So what we did is we took again, we were talking to Jose Valenti. I've said her name quite often now. So this is Jose Valenti's set of parameters for ruthenium trichloride. Okay, so she tells us, or they tell us, that you need a K, which is given by -5 millielectron volts. You have a J1, a J3, these gamma terms, which are here, etc. So this is the you have to know what the G factors are, which come from this papers, etc. But in principle, this is what people claim to be a realistic model of ruthenium trichloride. Okay, so we just take this without thinking too much, to be very honest, and we just do the calculation, and that's something bad happened here. Okay, and so this is the result of a comparison of experiment and Monte Carlo. Okay, so what is remarkable is we can go to temperatures where there is an overlap between the temperature scale of the Monte Carlo and the experiment. So this is the experimental scale. This is the Monte Carlo scale. So we can go much higher, of course, but there is this overlap. This overlap from blue to sort of reddish here. You see that what they measure is something like that, and what we get is this. So what this plots is B divided by T, and this magnetotropic coefficient divided by T. You will also see that the data here is normalized per ruthenium atom. Our data here is normalized per site, so that's per spin. And you see that even the scales work well, right? It's a bit scary now, right? It's a bit too good to be true, but that's what we get. And then what is beautiful is that they have claimed there's something something pretty interesting in the data, is that pretty unique, is that if you plot B over T and K over T, then you see something which looks like universal, some type of collapse, right? Now, if you go to higher temperatures, you see that this thing is peeling off. So this we can reproduce, right? This is the same color for the Monte Carlo. We can sort of reproduce this. And now, what they cannot do, because they don't have enough magnetic field in the lab, is that they cannot go to high temperatures and big magnetic field to see if this is a high temperature behavior or really a low temperature behavior. So that's what we can fill in. And we can fill in with the Monte Carlo. We'll go to higher. There's no limit for us in the magnitude of the magnetic field. And we can go up here and we can see that we can see this peeling off here. It's maybe a bit different, but nevertheless we can see it. And that there is another scaling here, which happens at high temperature. So the summary is that there is a scaling, K over T, B over T, for the very high temperature. There's a crossover to another sort of scaling at low temperatures. That's if you put everything together, that's what you get. Okay, so is this unique or not? That's important. That's important. So what is this scaling? B over T, K over T. What does it mean? There's one thing which is very easy. If you just take a single spin, right? You just take a single spin with G factors which are anisotropic, right? And then you do the calculation of this magnetotropic coefficient, then you will get this B over T, B over T scaling. Okay? So this is a property of an isolated magnetic moment. If you have an isolated magnetic moment, then you will get this scaling. So if you compare now the high temperature results, this is the Curie susceptibility. So this is the Curie susceptibility as a function of T, the spin susceptibility as a function of T. And then you see this 1 over T behavior here, which tells that you have something like a free spin. You had extremely high temperatures. You just at temperatures which are higher, if you want, than the parameters in your model. And this says, well, at these temperatures, you do see this B over T scaling. Now, when you go to lower temperatures, we can go to 40K, as I told you before, you have a marked deviation from the Curie law, but nevertheless, you go back to another B over T scaling. Right? So this is something which the question, so these are measurements, this is the data, right? And so the question you ask yourself, what does it mean? What does it mean? And so we did some simulations, and what we could do is say, well, let's try different models, right? Let's try different models that don't have frustration, which we can simulate without without a sign problem. And then you see here is that these are the same beta over T, the magnetotropic susceptibility. You see that at very high temperatures, you have this B over T scaling. These are these red lines. These are different ferromagnetic, these are different parameters. This is not so important. But if you go to the low temperature, there's no way that you recover another type of B over T scaling. Right? This is not something you see in ordered magnets, right? So this is just a property of high temperature. So we tried to look at the torque, right? Essentially, d of f of d of 5 is just the torque, which is defined like that. And the fluctuations of the torque is what you measure in the magnetotropic susceptibility. And there are clear differences is that in those Kitaev type models, what you see is that, so these are fluctuations of the torque, which we measure as a function of distance and at our lowest temperature. And this is for the XXZ model where we do not see this low temperature collapse. And you see very nicely here that the torque does not develop somehow longer range fluctuations. It stays very much like a local moment. So this is the reason why you see this D over T scale. And if you look at this torque fluctuations in the XXZ model, you see that they sort of develop some short range interactions, which make it very different from a local moment. So what we learned from these simulations is that the simple reason why you see this B over T scaling at low temperature in the magnetotropic susceptibility is that the frustration does not allow for development of spin fluctuations at a local level. That's all, right? That's our understanding of what we learned from that. Okay? Good. So what's next? So we could do something very useful with this, right? So we're very happy, and we're continue to work with Brad and with Kim, and that's going to be very nice. And there's another thing which we can do, which is even more remarkable, I think. So the Debye temperature of these materials is pretty high, 200. The 200 versus the magnetic scale, which is 100. So up to you to choose if you are willing, with all the debates there are in those materials, if you're willing to give up on phonons, right? But they're there, right? So the question is, can we include phonons in these ways of doing Monte Carlo for first-rated spin systems? And what will they do to the sign problem? That's our figure of merit. So these are simulations which we can do. But for the moment, we're just playing with models again. So we go back to our Kitaev-Heisenberg model. And if we take 32 sites, and this is the sign we had for this, the electron phonon coupling is given. The sign was like this for 0.33 for this, which is for people who are doing numerics, no, this is not an issue, right? And then if you put in the electron phonon, lambda 0.1, then you have a sign which does not go down, right? Which is remarkable. That tells us that we can do our simulations down to the same temperature that we could do before with an electron phonon coupling and try to see what the differences are. So that's what we're doing now. Now let me also tell you one thing is that we started off with this method and say, well, we're maybe not going to be able to contribute anything, but this is now something again which is nice because at the beginning of the talk I told you Monte Carlo does not care about dimensions, right? So we don't really care if we put in phonons. The Hilbert space is infinite, but we don't care because we just do Monte Carlo. All other methods which work on these Kitaev models are Hamiltonian based, right? They're based on they have to confront if you want the Hilbert space, and then it's extremely hard for them, I think, to put in some phonons. So we're a bit lucky. We don't understand why the sign does not go down, but we checked, it's correct, and so we're going to try to be able to see electron phonon, the effect of electron phonon at high temperatures for these frustrated spin systems. Okay, so I'm done. You didn't stand up yet. Am I done? But there's some questions, no? Without questions? I'm done. Who cares? We can go to. I'm done. Here. So, anyways, this is it. So I'll take 8 minutes for my conclusion. We can do. So this is Monte Carlo is very versatile. It's heavy, etc. And I showed you how to. I hope you should be able to program it yourself. You can also use our package if you want. And then I showed you for the applications. These are the newest things we're doing. This is maybe not so new. This is very new. For frustrated spin system where we're very excited to be able to couple to phonons and be useful to Kim and Brad. And here for these dimensional mismatch Kondo systems where we can look at all the different type of quantum criticalities in heavy fermions. Thank you very much. Yeah. They have seen what? The plume of scattering near the gamma point. Yeah. By C Legler and scattering. Yeah. Actually, can you simulate that? I didn't understand the first. What did I have seen? Phonon scattering? No. Plume of magnetic scattering. Near the gamma point. Yes. I mean, that's what people claim to be arise from target crashing, right? Yeah. And so I was wondering whether we could try to see that. We haven't looked at that for the moment. No, we haven't looked at it. Yes, massive. Okay. But it's thank you for that's a very good question. So the way we do this is the worst possible way to simulate phonons, right? Okay, but it works. and so we have very long autocorrelation times, but you see, in a certain sense we're lucky because we're going to stay on small system sizes because we're stuck with the sample. So we can brute force them out. But we only know how to do it this way. So simulating phonons, there are many ways of simulating phonons in quantum Monte Carlo. One way is to just, okay, I will put this as a field and I will update the field like that. That's the straightforward way. Now, generically, this leads to very bad long autocorrelation times. And there's been a lot of work using machine learning trying to understand how to promote them. That's hard. Then so that's not a good way to go. The good way to go is to try to integrate out the phonons, right? When you integrate out the phonons, you get retarded interactions, and that's what Manuel did, right? And these are remarkable simulations. So what Manuel did here to get this, where am I? Here, for this dissipation induced in this paper here. What he did, these are remarkable simulations where you can go to very low temperatures and very high, and you don't have big correlation time. You integrate out the phonons and you get an retarded interaction. Right? And then you get much better codes. We already did that also for the SSH model. It's really worth it. If ever you do phonons, try to integrate them out. Yeah, we can, yeah, that's possible to integrate them out also. We have a paper on archive.
So how do you simulate the phonon interaction?
Well, how do we do it technically?
No, for model-wise, yeah.
So for the moment, we're still, okay, so I don't really understand. So I can tell you how we do it for this toy model. That's not the question you have, right? Or,
typically, one magnet intersects phonons, and you have this coordinate, and then
yeah, so this should be, everything should be in there, right? So this is, for the moment, we have Einstein phonon. So we should change our Einstein phonon to an acoustic phonon, I guess, right? That would be good, right? That we're trying this, it's hard, it's somehow a bit harder. And then you would have a phonon branch here, which would cross the spectrum of all this object, and it couples like this to the spin. That's it, spin powers. So in principle, we can answer your question. We have a bunch of spins like that. We have a phonon which is going through it. We can answer the question, what happens to the phonon dynamics when it crosses this continuum of fractionalized object or things like that, right? So that's the motivation. Right? We're still a bit far from that.
So I think this study on the determinant path is quite interesting. So do you think that there will be some difference if the determinant is replaced by an optic band?
Yes, it will be replaced because it will be changed. It will be changed because the quadratic band touching will. So you can answer the question yourself. Actually, I'm trying to answer it myself. It's just you say for this one, right?
Yes.
This one. Well, it depends. I think that I don't have it off head for a quadratic band touching. How does chi decay as a function of imaginary time? Is it 1 over tau to the fourth or 1 over tau to the squared? That's the question. That's the answer. That's the way. You see. You just if you have, I think if you have a quadratic band touching, I don't. That's a hard question. I don't know. And I'll tell you why I don't know. Because even if you have a quadratic band touching, the quadratic band, as far as I understand, is not preserved by symmetry, right? So you can always, even if you have a quadratic band touching, you can have some type of deformation which will split into 2 Dirac cones or 3 Dirac cones. No? So then it's very hard to see what will happen, right? So it's not the quadratic band touching is not enforced by symmetry. Is that correct? Right? I think so. I don't know. Try. But the first question you should ask is try to do this type of weak coupling analysis and see if something is relevant or not.
Transition from the same spin chain,
Yeah.
but coupled more like post-grain way through some dissipated path and maybe Fermion.
So that's
so
Tahun.
I was wondering whether maybe let me confine a question
Yeah.
to you. Do you know anything about the export of the critical behavior?
I don't. So I know that Tahun, after this, he worked a lot on Vesumino-Witten models coupled to dissipation, right? And has some papers on that. I haven't talked to him a lot about that.
But in the numerics, you have enough.
So in the numerics, we just have, for the moment, we just have we haven't changed the. I guess the question you're asking is to change the power, right? We haven't done that. This is a one-shot thing. You have to change the power of the ohmic bath here. Your 2 has to be floated, right?
But even just on the Fermion problem, it's just coupled to the Dirac.
So I'm a bit lost now. So you want to
So forget about what I said. Just come back to the.
this one. Okay. This one. Yes. So there we have some. So I'm getting lost myself. Here it is. This one. Yes. So Tarun did. So he's of course collaborating with this on this. Tarun did an RG calculation, put it to second order, and from there he could look at the critical point and also the exponent. It's a nu equals a 1/2 exponent, if I remember.
So you have some correlation function.
We're working on that. we're working on that. It's a very hard thing to do because we don't have an order parameter, right? So we really have to think about ways. So we're trying to, you see, we can get the correlation length exponent so that the relevant operator is this, of course, right? Because we tune it with JK. So if we measure the dimer-dimer correlation, we will measure the correlation length exponent. So we're doing this for the moment. We're really trying to see what the criticality is. But it's going to be very different from local quantum. It's a Lorentz invariant system, right? So I think it's not going to match directly to a we'll go together, right? I'm quite sure. So we're going to do all this. So Shaunach is looking now at these dimer-dimer correlations at the critical point to see X and T dependencies to check all these things, right? To see what type of transitions that can go.